the very basics of assembly, what the operations you can do are, how to do registers, how to interact with the stack, and we will also go over how to write assembly code, essentially structuring it like C and then breaking down the major commands you'd find in C. We'll then do an example or two and answer any questions afterwards. So to start, we'll start with what assembly is. So assembly is essentially the human readable version of machine code, where machine code is just, ones and zeros in giant files. Assembly is the text version of what those ones and zeros mean, where a byte operation might mean move EAX, EBX. And so this means that assembly is basically the lowest level that you can get to machine code. C is advanced, like combinations of assembly commands to make larger operations. And you'll see what I mean by that a little bit later. But what this means is that a lot of the things you'll find in C and in higher level programming languages don't exist here. And by the way, you guys are welcome to ask questions anytime throughout this. Just feel free to interrupt me as we go. So what I mean by not having the same structure as C is that everything in assembly is just binary. It's ones and zeros. There's no concept of integers versus characters or other things like that. The only main difference is addresses versus data. And so if you've learned about memory, you know that data is stored in memory at a specific address, and the address is usually represented in some hex value. But to assembly, this is still just a number. It's how we treat the data that we're representing that makes it a character or a string or an array for us. But to the program, to assembly, there's no such thing as data types. So you don't have to worry about conversion errors when you're compiling, stuff like that. On the flip side, you have to keep track of those conversions for the data that you want to present. And for example, Ascii codes, which we'll talk about briefly, have, to the computer, they're just numbers. But to us, we represent, character A as some hex number. And you need to keep track of, is this number a character? Or am I treating this number as a character, or am I treating it as a number, or as an address, or as anything else? So you need to keep track of your own data types is the moral of the story there. All right, let's get into the structure of an assembly file. So you've got three main sections. You've got the section.data, you have a section.bss, and you have a section.text. Now I think you're far enough in the class that you've seen this before, but essentially the section.data represents where you define constant variables or define variables. We'll start with that. We'll start with define constant variables. And what we mean by this are this can be strings, it can be magic numbers. If you remember from 201, magic numbers are any constant number that you use in your code. It can be terminating lines, terminating strings. It can be pretty much anything like that. Anything that you already know the value of will go here. Now the section BSS is the opposite, and these are reserving space and memory for future variables, for future data. So essentially, this is the equivalent of making a variable in C, and in C, for the .data section, you might say int a equals 1. and then you don't change the value of 1 throughout the thing. You just have this magic variable 1 in your code. But you might say you're going to read in a string from the user. You would say char array a equals, and my C is a little rusty here, but you might do something like that. Char array a equals, and then you might have, you just set it all to character zeros, where this is essentially a zeroed out array for a 3-character string that you're going to read in later. You don't know the value now, but what happens is when the computer starts up your program, it's gonna reserve this space in memory for a 3-slot thing. So essentially, you are creating spaces to store future variables, is what the BSS section is for. Then you have the .text section. This is where your actual code is going to be. Your .text section will have a label in it. It'll have multiple labels, but the labels are essentially marked addresses in your code that are stored in a table. And when you jump to labels, you will reference that table and essentially know where to go in your code. The .text section always has one label in, it's either start or main. So it's either one of these two. And it depends on, what compiler you're using. So there are 2 steps to compiling assembly because you don't have the niceties of C code. The first one is a linker, or an assembler. In this case, we use the NASM assembler. This will convert your assembly code into essentially the machine version of it. And what this outputs is a .o file. File.o. The next step you have to do is you have to link your code. And linking, one of the big things linking does is it actually combines multiple libraries. So if you, for example, use a C function, it has to be included and thrown into your file. And linking also does a couple other things to clean up your code. Now there are 2 different ways you can link. The first is using the dynamic linker, LD. And the second is to use GCC. If you use LD, then you need to use the start label. LD looks specifically for the start label as its entry point into your program. GCC is going to look for the main label. So you can use either of these, it just depends on what you want to use for your linking. The linker takes the .o and turns it into an executable file. You have to specify what architecture and the size of your memory space that you're working with when you compile code. And for, I believe, most of your 310 assignments, you're going to be using ELF32. And do I have it? Yeah, I have insert on. And you will be using 386. And essentially what this means is it specifies the width of your memory spaces. And it allows you to use EAX versus RAX, which we'll talk about the difference in a second. But RAX is a 64-bit register, so you'll need to use the 64 version that we had up earlier. Meanwhile, EAX is a 32-bit register, and you'll use the 32 versions. Now, if you're using 64, you can still use the 32, but it sets a maximum depending on which one you use. All right, so let's talk about registers. If there are any questions about this, you can just interrupt me as you please. So registers are hardware variables, are hardware implemented variables. And what this means is there is a set of transistors in the chip that holds data, and it is only, 32 or 64 bits wide, but it is a hard-coded variable, and it will always exist. And these are the things that you perform operations on. So when you want to perform operations on data, you have to load them into those hard-coded variable spaces and then perform the operations on them, because the operational logic inside the processor interacts with those transistors that make the register. So that's a slight hardware explanation. What you can think of in terms of code is that these are variables that you need to use to do operations, and we'll see some examples of that later. So the best way for me to show you registers are with a picture. So there's this nice picture from Virginia State in their comp sci program. As you can see here, you've got a bunch of different registers to use, and this is only some of them. But the main general purpose registers are EAX, EBX, ECX, and EDX. These are going to be used for almost all of your operations and pretty much everything else you do. Now, they come in a bunch of different sizes. As we said before, RAX, which isn't shown here, is 64 bits, but they all share the same transistor space, which means that these lower 8 bits AL, this is a register you can access in your assembly code, and it's the lower 8 bits of the entire EAX register. So if you put a variable or data in EAX, and it's 32 bits long, and then you put a variable or data in AL, it's going to change the lower 8 bits of EAX. So you have to keep track when you're writing code. Am I already using EAX? If so, I don't want to write to AL. I don't want to write a different data point to AL because it'll change my value of EAX. So EAX has the lower 8 bits AL, the upper 8 bits AH, and these 16 bits together form AX. And then EAX is an additional 16 bits on it, so it's this larger section. And then RAX is actually double this size. They add another whole 32 bits. But you can't access these upper portions of it. You can only access these lower portions by accessing the lower sized registers. Each of these has a general purpose use. The ECX is generally called the counter register because we use it for incrementing and loop iterator variables. And there are actually hardware implementations of operands that allow us to do increments slightly faster or with a little more efficiency if we use this register specifically. Then you have EAX, which is I think called the accumulator register. This is used as the result for most of your arithmetic operations. They are stored in EAX, but we'll see that a little later. Another thing worth pointing out are ESI and EDI. These are primarily used for copying large pieces of data. So ESI is the source index and EDI would be the destination index. And we'll see that in use in a string operator a little later. These are also general purpose, so you don't have to use any of these for a specific thing, but this is like the general idea for how they came up with these registers. And then if you've heard of the stack, you have 2 pointers to the stack, one at the bottom and one at the top. The top one will be moved every time you add or remove the data from the stack. That's the ESP, the stack pointer. And then EBP, the base pointer, points to the bottom of the stack so that you have a reference of how large your stack is and when your stack is empty, because it'll be empty when these two point to the same address. All right, so let's get into some code. And I'm just going to hit enter a couple times. So we need to build introduce some operands that we can use for our normal day-to-day coding and assembly. The first and probably most heavily used is going to be the move operand. This is essentially, or I guess they're called instructions. The move instruction is going to copy data from one location to another. So it's going to copy data from a destination address to a source address. And these can be registers, these can be variables declared in .data or .bss. And you'll see plenty of examples as you work on this. You'll become very familiar with move. There are a couple other versions of move, and these have to do with the size of the data you're moving in. The first is move ZX, and this is used to zero out the rest of the register that's unused. So for example, if I say move ZX EAX3, this is going to put the binary version of 3, which is 1, 1, into a 32-bit register. So we're only using 2 of those bits. It's going to zero out the rest of them. Now it'll probably already do that, but when you're doing something like pulling from memory or telling it to, for example, move ZX EAX byte pointer EBX. What this line means is that we are grabbing 1 byte from the address stored in EBX. And for example, EBX could be an array, such as this A thing we saw here. We only want to grab 1 byte. But EAX is 4 bytes in size, 32 bits. So we're going to zero out the other unused bytes in EAX. The brackets are used for dereferencing. If you've heard of that in C, essentially, this is an address. You want the data stored at the address, so you use the brackets. These are going to be used for both data and BSS variables. And if you're ever working with code and you try to grab data and it comes out as an address, just know that you probably need to switch the brackets because you might be using them in the wrong situation, or you might not be using them when you need them. There's another one, move SX. And what this one does is the exact same thing as zero extend, except it's sign extend. So if you put in a negative number that's only 1 byte in size, but you have a 4-byte register, it's going to sign extend up to the end of that register. All right, so that's move. You have bitwise operations such as and. You also have OR, XOR, and test. So all of these are bitwise operations, which means they don't go byte by byte. They actually look at the individual bits in the 2 datas you give it. And is going to AND thing A, thing B, and store it in A. OR will do the same thing. XOR will do the same thing. Test, on the other hand, won't change the destination register. Test is going to check whether or not they're the same thing. And so what we can do is say test EAX, EAX. And test is going to, this line will check whether EAX equals 0. And it won't change the value of EAX either. It only updates the flags register. We'll talk about the flags in a second. You also have I'm going to hit enter a bunch of times so I can type in the center of the screen. You also have your arithmetic operations. So you have add EAX EBX, which is just EAX equals EAX plus EBX. You have subtract EAX, and you can use, this is just an example, you can use constants or you can use variables, it doesn't make a difference. By the way, the semicolon is a comment, it's not the end of a line like in C. So you have subtract EAX, which says EAX equals EAX minus 15. You have multiply, and multiply and divide are a little different. You would move AX 15, and then you would multiply BX. And what this is saying is DX colon AX equals AX times BX. So the reason we have, and this is why it's called the accumulator register, is because it's the set destination. You can't tell it to store it somewhere else. It always stores it in the A register. Now what we have here is this dx colon ax. This is because multiplying two 16-bit registers together might give you an answer that's more than 16 bits in size. And so anything greater, the lower 16 bits of that result would be stored in AX, and the upper 16 bits would be stored in DX. This is important if you're multiplying two big numbers together, because you always need to take into account the DX. In a similar situation, divide is going to say AX remainder DX equals DX AX over BX. So this is saying I might have a 32-bit value that I want to divide by 16 bits, and the result is going to be stored in AX with the remainder stored in DX. So again, this is so that we can do larger sizes of variables in these operations. And this extends out to the larger pieces as well. I can make this EDX, EAX. So now I can have a 64-bit output. And I can do the same thing with the R, the 64-bit sizes. All right. So that's multiply and divide, and those are our arithmetic operations. I'm going to talk about something a little different now. We're going to talk about the flags register. So the flags register has a whole bunch of, it's the same idea as a register as EAX or EBX, except each bit in here means something specific. So for example, there is the carry flag bit. So the carry flag bit just says, does the operation result in a carry over? You have the, and in this case, a 1 is a yes, 0 is a no. And so at the end of all of these arithmetic operations, the flags register is updated, where maybe there is a divide by 0, and that's an error, that's a flags register. Or you add two big numbers, there's going to be a carry, or there might be an overflow flag. Yep, I'll talk about int x80 as well. All right, by the way, does anyone have to leave at 1 o'clock? Because we're getting close and I still have some stuff to cover. Okay, if you do, then just tune into the YouTube video that we'll post afterwards to catch the rest. So all these flags are really important, and I'm going to write a few of them out. You also have the 0 flag, where if the result of your operation ends in a 0, the 0 flag will be set to 1. And this could be, for example, 15 minus 15 equals 0. The 0 flag gets set in this operation. You have the sign flag, which I believe covers a sign change, but you can double check me on that. It either covers a sign change or it says, is the result negative or positive? Positive, 0. And did I miss one? Yes, I did. Parity flag. And 1 is even, 0 is odd. Now, there are a bunch of others besides just these couple, but these are the most frequently used, especially in your class. And they're used primarily in our jump operations. So jump will jump to a specific label. And this is used to add structure to your code, to skip lines, to create program flow that isn't just linear. But you can have conditional jumps as well. For example, jump equal label. What this will say is jump equal will say if the previous operation above this line resulted in two things equaling each other, which would be a 0 flag of 1, because 15 minus 15 is 0. They're the same. These two are the same. The jump equal will only jump if the previous operation resulted in an equals. There's the alternative, jump not equal. And what this says is if the two are not equal, do that thing. And these conditional jumps check certain flags in the flag register to determine exactly what happened in the last operation. I'll write out a couple others. There's jump 0, which does the exact same thing as the other one. I can go over bit masking and shifting as well. All right, and I'm just going to copy a big list over from my thing. Boop. So you've got all these different operations, and it can be everything from jump carry, jump overflow, jump above, jump below, and you'll notice that they have like jump less than, jump greater than, which is very similar to jump above, jump below. So they have a lot of redundant operations as well, redundant instructions. Worth noting is that you can add an n in here to any of these to get its opposite. So as I showed above, jump 0 can become jump not 0, jump not carry, jump not overflow, jump not greater than, jump not below or equal to, which would be the same thing as jump above. So you can really just add ends to any of these and you can get the opposite thing. So you have a wide variety of jump operations. All right, so let's talk about a little bit more complex of a jump operation, and that is call. So calling a label will actually save the current location in your code so that you can return back to this. And this is the idea of in C, you might have int a equals 3, and then int b equals 4, and then you would call print, and you would say print hello. So calling this function is actually going to use the call operation. If you were to disassemble this code, you would see call being used right when print is called. Now, what this does is it returns a pointer to this line of code. So it saves this location in code so that when you go to wherever the print code is in your file, you can return back to this point and continue on with the next line of code. And the way it does that is by using the stack, which we'll talk about soon. The stack will say pop, or we'll say push RIP. RIP is the instruction pointer, and it holds the current address of the instruction you are using. So for example, if I'm running through a sample code, if I'm running through assembly code, every time I complete an instruction, the instruction pointer gets incremented by 1 to go to the next instruction. So you don't want to use the instruction pointer as a general purpose register. This is something you really don't want to mess with unless you're doing something like a call or a jump. And then you have jump to label. So that's the code breakdown of our call operation. And then when you want to return from wherever you jump to, you just type ret. And the breakdown for ret is pop RIP. So what that's going to do is it's going to remove the address to the next line of code that we put on the stack, put it in instruction pointer. Now, if we have, let's say we have some example code, we'll just copy this line a couple times so that we have a couple lines. Let's say that we have our call right here. That means that when we call this, line 78 is going to be pushed onto the stack. So when we want to return, you might think, oh, we're going to return to line 78. But remember, at the end of this line of code it's going to say, I'm going to go to the next line of code. So I'm going to increment my instruction pointer, the address in my instruction pointer. But the address isn't pointing to line 75 anymore. It's pointing to line 78. So when this line finishes, we have loaded 78 into our instruction pointer, and then we have incremented to 79. So you don't have to jump after this. I hope that makes sense to people. All right, so the next thing we're going to talk about is the compare operation. So compare operation, you can compare between two registers, you can compare between a register and constant, you can compare between addresses, a whole bunch of stuff. Now, all compare is EAX minus EBX. And it doesn't store this anywhere. Like it doesn't update EAX to store the subtraction, but it updates the flags register. So if you have EAX minus EBX, if EAX is greater than EBX, then you're left with a positive number. If EAX is less, then you'll be left with a negative number. If they're the same, you're left with 0. And so the 0 flag would be updated, or the negative flag would be set. And that is how the compare operation works. It updates the flags register so that what you'll typically see in code is you'll see like compare EAX to 5, and then jump above to some label. What this says is if EAX is greater than 5, we're going to jump. Otherwise, we're going to continue on to line 91. So the compare operation just updates the flags register. You generally want to do your decision, your jump, your conditional jump, right after the compare, because let's say you do a compare and then you do an add. Add will update the flags register, and then you're not going to have the jump above isn't going to be jumping based on the flags of compare. It's going to be jumping based on the flags of add. So you want your jump right after your compare. All right, let's get back to the center of the file here. So the compare uses the 0 and the carry flag for its operations. Let's talk about shifting. So if you remember from Comp 212, shifting is basically saying I have this 8-bit value and I can shift, which is going to be, I can shift right, which will be 0, essentially moving all the bits to the right one and inserting a 0. I can shift left, which would be 1, and inserting a 0 at the front. I can rotate, which is essentially going to say left or right, we'll use left. So if I rotate left, the 1 that I remove comes over to the front, and rotating right will do the same thing. So there are commands that actually do these things. There is shift right, EAX 1, and this tells us to shift EAX right by 1 bit. So this can be like 4, and it'll shift it right 4 bits.
I thought EAX1, SHR EAX1 added a 0 at the end to shift. So it would like multiply the whole thing by 2.
Well, that is technically correct. So the shifts are adds or divides by 2. For example, if we have this number and then we shift it left, that is a multiply by 2 in the binary realm. And then if we have this value and we shift it right, that's a divide by 2. So this is a quick and neat way to divide by a certain number of 2s. You can divide by 256 if you do 8.
Wouldn't you need another 1 in line 97 for it to be line 95 times 2? I may be mistaken.
You're right, but keep in mind that if we're only working in an 8-bit register, we're going to lose that upper bit.
Okay.
And we'll actually get an overflow. And the flags, this actually goes into the carry flag bit. because we get a carryover operation. Am I
Okay.
backwards?
Yeah, that makes sense. Thank
Oh,
you.
no, I think, yep, no worries. I think he's saying that you are backwards to more. Yeah, yep, that's correct now. Shift right is a divide, shift left is a multiply. And then, so there's shift right, there's shift left, there is this guy, which I don't know what it's called. I call it signed arithmetic right because it's the exact same thing as a shift right, except it's going to keep the sign as you go. So if we have our value here, technically since there's a 1 up here, this means this is a negative number. So if we shift this right, it's going to put a 1 in that uppermost bit to keep the sign correct. And then SAL will rotate left, but since the sign is never determined by the least significant bit, it's always going to put a 0 in. If you had a positive number here, like 0, 1, like that, it would, this SAR would be 0, 0, 1. It would input a 0 because the greatest one is a 0. So its sign extends your shift, left or right. Yeah, arithmetic shift right. Thank you, Colby. So that's shift. I believe there is actually a rotate operation. We do a quick Google. We find that there is, yes. Here we go. Rotate right, and rotate left, I believe are the two. Yep. So this is going to do this rotate operation that we talked about here, where the 1 gets brought around. And so those are your rotates and your shift operations. And I'm just going to shrink this a bit. All right. And you can think it's rotate because it sounds like roll. You're rolling the bit. You're rolling the thing around, which is a cool little thing, you know. All right. Yeah, we can talk about masking. Da, da, da. Okay, so yeah, masking is actually pretty important, especially for some stuff that you'll learn later on. I think I used it in some later 310 projects. So let's say we have a 8-bit string like this, and we only care about these 2 bits right here. What we can do is we can use a bit mask, and a bit mask for this thing would look like that. And so if we want, a mask is essentially used to extract only the data you care about. And if we only want these 2, then what we can do is we can AND it with this. So the bitwise AND operation between these 2 would be 0, 0, 1, 0, and all zeros. And what this leaves you with is just the stuff you care about. So let's say we have a, oh, here's a really good example. Let's say we have a 32-bit value right here, and this is stored in EAX. So EAX is a 32-bit register. It stores this 32-bit value. Is this 32? No, this is 16. We need to copy it again. All right, 32-bit value. Let's say we want to access the upper 16 bits. Well, as we saw in the picture, I will throw it over real quick. As we saw in this picture here, there's no register name for the upper 16 bits of EAX. There are for the lower 16 bits, but there's nothing for the upper 16 bits. So what we can do is we can actually say, and the bitwise AND operation, EAX with 0, 0. So this is the hex version of all ones in the upper 16 bits. Is that right? No, we need twice as many. So what this will do is you're going to AND this with the all ones in the upper 16 and all zeros in the lower 16. And this will leave EAX looking like this, where the lower 16 bits are all 0, the upper 16 bits are all 1s. And what we can do then is just a shift right EAX 16. And then now AX holds this data that we care about. Now you can also do this simpler by just shift writing in the beginning, and then it will automatically zero out all the zeros that it puts in front of here, and you will just be left with the 10101 stuff here. But this is just a basic example of how you can use a mask to extract specific data from a register bitwise. I hope that explains masking for you guys.
So, so the position that you want, like the bits to be captured, you put those as a 1, and then everything else is a 0, and then you AND it together, and it keeps what you want.
Correct. Yep.
Okay.
Okay, so the next thing we're going to talk about is system calls. So this is a pretty cool and slightly advanced topic for assembly, but essentially system calls say we are a program operating in an operating system or interacting with a kernel, the kernel being the core of the operating system that controls hardware and stuff like that. And our program is only permissioned to do certain things and access certain memory and do stuff like that. Some of it is security, some of it is protection against us from like harming ourselves or our hardware. Essentially, the kernel limits stuff we can do. And this can be things like interacting with files stored on the hard drive, interacting with the user through standard I/O, getting user input from standard in. Those are things that we can't really do right away. We don't necessarily have permission to do that unless we are the kernel. The way we get around that is we ask the kernel to do those things for us. And that's what a system call is. A system call is saying, I'm going to relinquish control of the processor and give control back to the kernel so that the kernel can run. And I'm going to ask the kernel to do something for me. And the example for that is, let's do the easiest example, which you've probably seen before. Move EAX1 int 0x80. So if you've seen this before, you might have seen 80H instead. What this is saying, this is an interrupt. So an interrupt is going to raise a flag for the kernel, and the kernel will freeze and say, I need to handle this. This is a important event that has occurred. And you'll learn about hardware interrupts, which are essentially, you're doing stuff and then raise a flag when you need to be handled by the processor. And that can be like memory is ready or your arithmetic side processor thing, I forget what it's called, is it's finished its operation and it's ready for you to grab the output data. So I'm going to raise an interrupt flag. Your mouse will raise interrupts over the USB system saying, hey, I have data, or the keyboard, right? When you press a key will create, yeah, the floating point code processor. That's what I meant. Thank you, Timur. Yeah, your keyboard, when you press a button, will create an interrupt. Yep, that's Colby's posted a good picture. So this basically invokes the kernel, and then the kernel has to figure out what you want it to do. And the way it figures it out is the registers. So each register is a specific input, and it's just like calling a function. Let's say we did in C, we called, let's do print. And let's say we gave it 3 arguments. Actually, we won't use print. Let's call this just function. We gave it 3 arguments. If we called this is the same idea as us calling the kernel and saying, hey, we need you to do something for us. And the arguments here are going to be stored in the registers. And you can see what each one is. There's a nice little example, there's a nice little table, and there are a lot more than this, but this essentially says, here are the system calls that we want to do, and they're enumerated by EAX. This is the name of the system call, and then these are going to be our inputs into it. So EBX, this is going to be the return value of our program. So if we set EAX to 1, which we did right there, EAX equals 1, this is going to be a sys exit. So we're telling us to exit our program, to quit our program, close it out. And the return value could be 0 on success, 1 on error, stuff like that. If you ever run your code and it says like program ended successfully with 0, that means that you've returned 0 from main. That's the standard for like a successful run. You can also do things like sysread and syswrite. Or if you want to open and close a file, you can use sysopen and sysclose. Now, what you do is you set up the registers with what you want to tell it to do, and then you invoke the kernel. And as you can see, that's what we did here. We set EAX to 1, then we invoke the kernel to exit. If we want to sysread or syswrite, we also have to set up these things as well with, for sysread and syswrite, this is going to be the file descriptor. So the destination where we want to write to. And it can either be a file pointer or a file descriptor that we get from sysopen or sysclose to write or read from a file, or it can be 1. The value 1, I believe, is standard IO and standard IO. So if we want to read or write, we set this to 1, and then we give it the pointer to our string array or our char array that we are going to tell it to write, and we give it the size. So this is the exact same thing as if you called print in C, print, you would have to say standard in, maybe we have a string called hello world, and it is of size X. So that would be the C equivalent of doing this in assembly, where we set the length of the message into EDX, we set the message itself into ECX, and I'll pull this over so you can see it. We set the message into ECX. EBX is set to standard in of 1, and EAX, which is going to be the operation we want to do, is print. So I hope that makes sense. That's what you're doing when you ever see an int x80, and it can be used to quit, to read, to write, to when you get into OS, it'll do more advanced stuff. In 3.11, it'll do more advanced stuff. So just be aware of those. Now you can only do this if you have a kernel, right? If you're writing Arduino code or microcontroller code in assembly, there's no operating system to call. You have to do that stuff yourself. And you'll learn how to do all that in Compy 3.11. Yes, this changes the values in registers. So keep in mind that it needs to store stuff somewhere. And for example, read is a good example. If we wanted to read from standard IO, actually I think it's called standard in. If we want to read from standard in, it's going to change this thing, and it's going to change the number of bytes that it read. And so it's going to update ECX, and it's going to update other stuff as well. So always make sure that if you have values stored in your registers, you want to save them before you do that. Thank you, Colby and Tamora, for pointing that out. And you can actually look online to see like what registers they change when you are writing your code. All right, so that's a lot of talking. Let's take a look at a hello world program. Let's make a program, and I'm gonna make a bunch more enters so that we have a nice clean file to look at. All right, so we are gonna start with our sections. So we have a section.data, section.bss, and a section.text. So in our section.data, we're doing hello world. We already know what we want to output. We want to output a string. So we might say, oops. Okay, so here's our string db. What this says is declare a byte, which means that every step in our size is going to be 1 byte in size. And we're going to store the address to this variable in the variable string. Now, what you'll commonly see with strings is $$ minus the variable name string. What this means is you want to get the length in bytes is equal to some arithmetic operation. Now, string is an address, and it points to, technically, it's going to point to this H right here. So if we want the length of it, we're going to start from the current address location in memory, and we're going to subtract the address of H. So if H is stored at like 0xFF00, then it would be 0, 1, 2, 3, 4, 5, the space would be 5, 6, 7, 8, 9, 10, 11. So 0xFF0A. So we subtract, A isn't 11, I think B is 11. So it would be FF0B minus FF00, which just equals B technically, but that's 11. So now we know the size of our string is 11. So that's how the EQU thing works. And we want a new line at the end of this, so we can either just say 0xa, and in this case we are just going to do 0xa. Oh, we're going to keep our BSS section. We don't need anything in the BSS section, so in this case we're just going to get rid of it. And we also want to say global underscore start. This isn't necessary, but it just says like a start is going to be globally known outside of text. And it's not something that you really need to worry about, but it's something that you can put in here. All right, so what do we need to do in this hello world? We need to print out. Well, we just saw the code to print something out. And we know from our little table here that we are going to use, I'll pull it over a little bit. We are going to use system right. So let's go ahead and move 4 into EAX to say that we want to use system right. Let's move 1 into BX to say that we want to use standard IO, so standard out in this case. And let's move the pointer to our string into ECX, so in this case the const char, which is just going to be str. And EDX holds the length, so len. And int 0x80. And then to exit after that, because we're done, we have to exit. So we'll say move EAX1 0x80. And this will run our code. This will print out hello world on the screen. So that's what a basic thing would look like. Let's talk about something a little more advanced. And this is going to get into structured code. So let's say we want to do an if statement. In C, that would look like if x equals a, and we're just going to say int x equals 3, int a equals b, 4, and we're going to say int c equals 0. All right, so if x equals a, then we want to say c equals c plus 1. We'll do c plus a. Else if, I believe that's the proper syntax for C. I'm a little rusty, but else if x equals b, and technically it would be double equals, I'm remembering now. X equals b, and we need end curly braces. Yeah, don't judge me on my C. I'm a little out of practice. All right, so we're gonna say C equals. We don't have a B. We'll make a B. C equals B. Otherwise, else. C equals 1. So this is our if statement. It looks pretty simple. It's got an if, an else if, and an else in C. Let's talk about how we'll write that in assembly. So the first thing I'll do whenever I look at a block of code is, and whenever I want to write a structured block of code like this, is I say, what variables do I need to use? And in this case, we have 4 variables, x, a, b, and c. So I'm going to say, and I'll usually write comments at the top of each one. I'll say EAX is going to be x, not XOR. I'll say EBX is going to be A. I'll say ECX is going to be B. And I'll say EDX is going to be C. So now I know which variable is doing what. And in more advanced situations, we can say like ECX is going to be our iterating pointer through an array, or EBX is going to be something else. But what this helps me do is when I now write my code and I need to use a new variable, I already know which registers are in use. So I know I can't set them equal to that. I have to use a different variable. So this is always something I'd recommend, especially when you're starting out with assembly programming. All right, so we already know what an if looks like. It is a compare followed by a conditional jump. So in this case, we're going to compare x, which is EAX, to a, which is EBX. And we're going to jump equal to some space. Now, here's what we need, right? We know that there's another else if. So that's another compare somewhere else, right? We'll put it right here. Compare EAX to ECX in this case, and some sort of jump. So let's put this in a label so that it's a little more structured. Now, as we remember, assembly is linearly running, which means it's always going line by line. And it doesn't have, the structure where if this is false, it's going to skip these lines. We have to build that. So what I might do is I'll say, I want my code for inside this first if statement to be right here. And I'm going to make that a jump not equal to, we'll call this if else. Actually, we'll call it else if. So now what this says is if these two are not equal, jump to the next condition. And here's the next condition. We'll do the same thing. If these two are not equal, which will be the false for this conditional, we're going to jump to else. And I'm going to make it a label called else. And in this one, we are just moving edx1. That's our else condition. So now you can hopefully see kind of how it's structured and how it almost resembles an if statement. And this is exactly what the assembly breakdown of if statements are like. This is how they came up with C. They said, we've got this pattern here that we're seeing very frequently in our code and assembly. Let's turn it into something easier to use. And that's how they came up with things for C. So let's just complete this real quick. ECX. Actually, we're going to add ECX and EBX. In this case, we're going to ECX and oh no, C is D, so D, CX. So here's our complete if statement, the complete assembly version of this if statement right here. So we're going to go over we're going to go over something a little complex. We're going to do for loops next. Okay, so let's look at for loops now. So let's make a for loop in C first, and this is something I would recommend when you're writing assembly, is write out what you want to write in C and then do each block of code. So for loop would look like int x equals 0, x is less than 5, x plus plus. And then inside this, what are we going to do? Let's print out our value of x. Yeah, let's just loop through and print out the value of x. So in C, that might be print x. And I think you have to convert it to a char. Again, don't remember if that's the exact thing for C, but this is essentially the pseudocode of what we want to do. We're going to print out x as we go. We should see x print out 0, 1, 2, 3, 4. Okay, so let's talk about how we're going to do this in assembly. Well, to start, we know that we need some sort of, we know that we're going to be printing, right? So we know we're going to have to use syswrite. So that means that EAX, EBX, ECX, and EDX are all going to be important for syswrite within the loop. So let's go ahead and underscore start. Okay. So what do we know? We know that EAX is going to be used. We're going to EAX, EBX, ECX, and EDX are all going to be used for syswrite. So we know we can't use any of those, but we have one variable here. We have this incrementer variable. So let's use a different register for that. Let's use EDI is for x in this case. Now, in old C, you used to not be able to put the definition of the variable in the for loop. You had to put it above. And so our for loop looked like that. And technically, I believe they had x equals 0 here if you wanted to. But you couldn't declare x. You couldn't make the new variable inside here. And I like this syntax because in assembly, you have to do the same thing. Before you start the loop, you need to say XOR EDI. Now, XORing something with itself will zero it out, and it's actually a faster operation than using the clear or delete operations from that are built into assembly. All right, So let's make a label for the start of our loop, loop 1, and we don't need the underscore. All right, so what do we do in our loop? We do the same code to print that we do before. So I'm just going to copy it from above. Here it is. Boop. So inside our loop, we're going to set EAX to 4, EBX to 1, ECX we're going to set to something, we're not sure yet, and EDX is going to be the length, and we are also not sure about that yet either.
这个东西我们到时候再看一下步骤。你干嘛在解什么？这是谁做的？
Tracy, your mic is okay. Thank you. So let's figure out how we get these things. Now we can't just print out EDI because EDI is a number, right? We need to convert it to the string representation, which to assembly isn't going to mean anything. It's just going to be a number. But to us, it's going to be readable ASCII. So the way we do that is we can actually say add EDI character 0. So character 0, if you add that to any single digit number in number stuff, it will number stuff. If you add that to any single digit number, it is going to make the ASCII version of that digit. And you can do that by looking at the ASCII table. ASCII table. Boom. If we zoom in, we see the character version of 1 is right here. Character version of 1 is 49. And character version of 0 is 48. So the value, the literal value 1 plus 48 equals 49, which is the ASCII version. So what does that tell us? That means that now EDI holds the ASCII version of our counter, of x. So now we can just tell it to print out the value in EDI. And we're supposed to give it an address, so you might have to use brackets, but we'll test that later. The next thing is EDX. EDX is going to be the size. We're just going to hard code that because we know the size of our thing, and that is going to be 1. It's only 1 byte in size. It's a single character. And then we call it int x80. It's going to print out the character version of our loop counter, which starts at 0. Now, right now, it is still a character, so we're going to subtract character 0 from it. So now it's back to the number version of our loop counter. Now, for loops will automatically increment the variable for you based on what you put here. We have to do that ourselves. So very much for loops and while loops are completely identical in assembly. So we're going to increment it ourselves. We're going to say there are 2 ways to do that. You can say add EDI1, or you can say increment EDI. Either one will work. We're going to use add EDI1 in this case. The next step is going to be to do our conditional, right? So we have the x equals 0 at the start, before the loop, outside the loop. You want it outside the loop, otherwise it'll just set to 0 always and loop forever. We have our conditional. Oh, we don't have that yet. We have our increment, which is right here, and we have our operation in the middle. So now we need to add the conditional to complete our setup. So very easy, we just say compare EDI to 5, and we will say jump less than to loop 1. And this, all these lines are the for loop representation of a for loop in C. So what do we have? We have the initialization of our looping variable outside of our loop label. We have the we have the condition right here that it's going to jump less than back to our loop. And if the condition is not met, it's going to continue down to this code, whatever code is after the loop. We have, I'll just put outside of loop down here. We have our increment, x++, we have that right here. And we have the operation that we wanted to do, which is all this stuff in the middle. So I hope that makes sense to people about how we essentially looked at a block of code in C, figured out what the variables we needed to use were, so that we made sure we weren't using the same variable for two different things. We figured out the things that the structure of the code did, being the increment and the conditional and the initializing to 0, and then we figured out how to do the actual functional stuff in the middle. So that's how you can work from C back to assembly. All right, that is all I had for now. I can do one more example if you guys want, or we can go to questions if people have any questions. Calling C functions, that is a good one to work with. And what you guys are probably talking about, if I remember the projects correctly, is printf. So let's look up printfc. And let's find a good one. This is not a good one. What about this guy? Okay, here's a good one. Boop. So printf is actually slightly different than your standard function. And we'll do a standard function first. This is just the formal definition of a function in C, of the printf function. So a standard function is actually going to have, let's do int function, int A, int B, int C. So let's say we have a function like this in C, and we can look into floating point units. This is also taking a bit, so I might do a separate one on FPU because they are a little complex when it comes to. You guys will have a project later on, and it's quite difficult. So floating point units might be a separate crash course. All right, so let's say we have a function C right here. We are going to, the general situation for functions in C is that these are, and this was the old way they did it, these are registers. Just like how the syscalls, these were registers. So, and it depends on what C function you're calling. You usually want to look it up to check and see which way they do it. The old way was that this meant you had to do the exact same thing that we did here when calling syswrite. And actually, you can write the C definition out for syswrite. Boop. Let's see if I can find it. Here is the actual C definition for write. So as you can see, it's the exact same thing as what we have right here, where syswrite has a unsigned int input, which is actually this int file descriptor. It has the char star here. This is a slightly different version than the system call that's defined in the kernel code, but it gets the same idea across, and it has the SciST, the amount. And this will actually update EAX with how many bits it wrote, and it does that in syswrite as well. So this is an example of how the registers are used as inputs. What most modern C functions do nowadays, and printf is a perfect example, is each of these inputs, since there can be, any number of input arguments, are actually put on the stack. So I'm not sure if you guys have learned a lot about the stack yet, but the way you would call printf, let's say we want to do printf This is a test, %d, %d, %d. So we want to do 3 numbers, a, b, and c, ints, 3 ints. If we want to do this, we have to push each variable pointer onto the stack in assembly because it's going to read it in the desired order. And there are a couple examples online, but let's see if we can do this through just writing it in assembly. So let's say we have our section.data. We're going to declare message for this guy. And then we're going to declare A, 3, B, 5, and C, 8. Okay. So these are our variables. Again, no need for .bss section. So let's go right into the section.text with our _start. And what you have to note is that you actually have to do this in reverse order. You have to push them in reverse order, and we'll see why in a second. So to call printf, we are going to, first we'll put, I believe up at the top, we just say extern printf. And extern basically says the printf label is defined somewhere else. We don't define it in this file. And it's used by the linker to say I need to find where printf is defined, and I need to insert the code for it right here. And so this line will expand out to include printf. All right, so boop, 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 boop. We will push the value C. Nope. We will push the value B. No. Autocomplete is screwing with me. We'll push A. And then we will push message. And I do not remember correctly, but you might need brackets around these to push the data value A, B, and C as opposed to the address of A, B, and C. And again, it might be backwards on that. The best way to check is to just check as you go. And now you can do this separately. If you want to, you can say move EAX to C and then push EAX if you wanted to. Either way works. This is a little bit cleaner in terms of how things work because this could be like a 1 byte in size. So you might do a move 0x. And stack pointer variables are always 32 bits in size, so it's a little cleaner. But the reason we don't push message first, you might think printf has message and then that, and that. It is actually because printf is going to do it the opposite way. So then we would call printf. And this is the general idea for how you would call pretty much any C function. Now let's look at what printf does. Let's say we look at the assembly for printf. Here's what they'll do. They are going to, printf is actually pretty complex, but the basic idea is it's going to take the first thing, which is the formatting string, by popping it off of the stack. So the first argument has to be on top because that's the first thing it's going to access. And yep, so thank you, Colby, for the code sample. This is correct. You will bracket these if they're declared in the .data. And he also, it's a good thing I forgot, you'll generally see something like add ESP 8. The reason, and in this case, it would actually be, it's 4 bytes per slot because each stack address is 4 bytes in size, in data size. So if we just had a message, it would be add ESP4. If we just had, since we have 1, 2, 3, 4, that's going to be 4, 8, 12, 16. What this line is saying is we're clearing the stack of all this stuff that we put on there, because printf isn't going to get rid of it. But it's good to maintain stack cleanliness. So we're going to get rid of the stack stuff that we added onto that. And remember, the stack grows upside down in memory. So to go backwards, to remove stuff from the stack, you add, and to go forwards, you subtract from the stack pointer address. All right, so yeah, printf, it's going to pop the first thing. And what printf actually does is it loops through and it prints character by character, right? So it's going to print out T, it's going to print out H, it's going to print out I, all the way till it hits a %sign. And then it finds out what data it needs to grab. It will pop the next piece of data from the stack, which it expects to be this one. And then it will convert it to the correct data type. Since we pushed it as an integer, it will convert it to a string for us. And then it will print it out. And then it will print out a space, and then it hits another %. It's going to pop the next thing from the stack, in this case B, and it's going to say, what do I need to do? I need to convert it to a string, blah, 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 print it out. But that's why it expects it in reverse order. And you'll find that all C functions are going to have their arguments pushed in reverse order, and that's just how it works, how they decided to do it. And what you'll typically see in the beginning of this statement is a when a C function is called, and let's say we were writing our own version of a C function, we would typically push the we make what's called a stack frame. And the idea of a stack frame is that we want to save all the previous variables to the stack and make our own stack, mini stack. And the way we do that is we would say push maybe EAX, push EBX, push ECX, push EDX. So any register that we're going to use in our code, we want to save the user's values so that we don't overwrite them. And then at the end of our code, we will see pop EAX, pop EDX, pop ECX, pop EBX. Again, backwards from the way we pushed it on. Okay. But since we're adding stuff, right? If we pop EAX, it's going to put the value of EDX in there. So what they usually do is they say push EBP. And remember, this points to the bottom of the stack. Or no, they don't. They say push ESP. And then they say move EBP. It is EBP, I'm sorry. They say push EBP, and they say move EBP ESP. So what this does is it says we're going to save the old bottom of the stack, and we will use classic Paint in this case. Paint 3D if you guys are part of that new Paint stuff. So here's our beautiful stack. We've got EBP pointing to the bottom, EBP, and then ESP is going to move up all of these values as we go. So ESP might be pointing to here. Well, when we push, let's see if I can do this side by side. If I get rid of this, can I get rid of it? I cannot. All right, we're going to drag it then. So when we push EBP, what we're doing is we're putting the old value, we'll call it EBP1, onto the stack. And now when we push, ESP automatically increments to the next point. And then we're going to say move ESP into EBP. So now ESP and EBP point to the same part. So from the perspective of our current stack, it looks like the stack starts here and goes up. It looks like an empty stack to us. And the benefit of this is that we don't have to worry about managing all this other stuff on the stack. We just have to worry about our stuff that we add here. I hope that makes sense to people. And it's actually the same way that the kernel calls your program. It will make a stack frame for you so that from your perspective, the stack is empty when in reality, there is a bunch of stuff down below. And when you run command line programs, the input arguments, say we ran a program like we ran your program /hello world, and we gave it an input argument 3 because we wanted it to print hello world 3 times. This value 3, this input argument, is actually stored down here outside of your stack frame, but it is on the stack. And so when you get to the point where you take input arguments in assembly, you'll see them accessing ESP like +5 or +8, and that's because they're going this way into the stack. And it's plus because, again, in memory, the physical addresses, the stack is upside down. This is the highest addressed, and this is the lowest addressed. Just a bit of a stack explanation, but this is called setting up a stack frame. These codes right here, and technically you would also have to add pop EBP. So this alone is a stack frame. And then in here we can do our normal code. But since we added all this stuff to the stack, our stack pointer is pointing way above where we push these messages. So what we have to do is we have to do ESP plus 4, 8, 12, 16, 32. So I believe 36 is the proper answer. But it's, so we would say move EAX ESP plus 36. And essentially what this is doing is it's saying go 36 bytes up the stack, or like 8 things. So 1, 2, 3, 4, 5, 6, 7 or 8 things to get to the thing that we pushed originally and put that in EAX. Now EAX stores the pointer to our message. And it's going to be the exact same thing when getting input arguments from the command line. You'll see a big thing like this, ESP plus a big number. Technically be 28 because we're going up 7 and in steps of 4. All right, so that is calling functions, and then it would do, since to complete printf, this would be all the other printing stuff that it does, its actual functionality. All right, are there any questions that need to be answered? Is there anything else that I can cover for you guys before we finish up here? I'll do floating points in a separate video and go pretty in depth into those because they can get kind of complicated. Yeah, we're an hour and a half in, so I think it's a good stopping point. I can also go over debugging if you guys want to see how to use GDB on an assembly program. That's a pretty helpful tool. Or we can save that for another crash course like next week where we do GDB and floating point units. Oh, okay. So just in case you guys are not familiar with it, this is technically part of IEEE. So if you go to umbc.edu/IEEE, we have a wonderful website with a whole bunch of resources for CompE and CompSci students. You just click on the resources tab up here. And there are things for assembly, there's stuff for programming, a whole bunch of other things. You're welcome. I'm glad you guys got something out of this review session. But yeah, this is a great place to get more information for pretty much any class you have and general stuff as well. You can also see some of the other things that we offer in our club as well, such as projects. But that's everything. I might post a consolidated version of the code we have in here in the Discord for you guys to have, but you will be able to reference this video on YouTube as well. All right, thank you very much for your time. I'll stick around maybe 5 or 10 minutes to answer questions if there are any stragglers. If not, have a great weekend and best of luck in your class. Ooh, YouTube channel, UMBC IEEE YouTube channel. You can just go to YouTube and Google it. It'll probably also be linked on our website as well. You are very, very welcome. You are welcome. And you can always ask questions in the Compy 310 chat on Discord to get help with specific assembly errors and other such things as well. Yeah, it's a pretty new channel. We're going to have a bunch of new videos up there soon. I think I'm going to be making quite a few things, ranging from assembly to circuits to operating systems and stuff. Pretty much whatever people need or request.